Dr. Darrell Gill is the Vice President at IBM. Dr. Gill received his PhD from MIT in electrical engineering and computer science. Now, as Vice President of IBM, he oversees the AI and quantum computing program at IBM. And before that, he was actually the VP of research, and he has actually overseen the 12 research laboratories at IBM. That's over 1,500 employees all over the world, and covers the basic science, physics, mathematics, together with industry solutions, including AI, IoT, quantum computing, and blockchain. So he has broad spectrum of knowledge in all of these areas. And with that, I would like to introduce Dr. Darrell Gill to the stage.
Thank you so much. Thank you. Thank you. Good morning. It is such an honor and a pleasure to be here in front of this community that has done so much to shape the past, the present, and of course, the future of computing. I'm showing a picture here once we can see the slides. Maybe I could go back. Okay. This is where I work, about 45 minutes north of Manhattan. This is the T.J. Watson Research Laboratory. It's the research headquarters of IBM, and we have about 2,000 scientists who work in this building. And today I'm going to focus my remarks fundamentally around AI, but with a twist. We are going to spend, I'll be able to describe where is the current state of affairs in AI and where we believe it needs to go. But I'll have a particular emphasis talking about the computational substrate for AI. And I'll get a chance to talk about, different architectures and analog computing, and also quantum computing as applied to AI. I'll start with this statement of AI being the new IT. And what I mean by this is that, in a way, if you've noticed the way the conversation is going on with AI, things that we used to talk very broadly around the world of information technology and automation, now everything is getting substituted by using AI, is doing this and doing that. And that's not necessarily a good thing. There's a lot of hype associated with this, but it's also a reality that is become, arguably the most important trend in the technology world today. And one indication of that fact, you see it in what's happening with students. So if you look at enrollment, as an example, at MIT and Stanford, to Introduction to Machine Learning, a class that maybe a decade ago may have had 30, 40 students, now has over 1,000 students enrolled at Stanford, over 700 at MIT. If you are in the business of recruiting students, you will notice that when you look at resumes right now, machine learning is one of the things everybody highlights. Like almost no matter what background people come in, right? They put machine learning in it. So what is it, and where does it need to go? Now, the field of AI, of course, is an enormously broad area that has been with us since the late 1950s. And within AI, we have machine learning. Within machine learning, we have a subfield of neural networks. And within neural networks, we have the thing that is all the rage of the recent years, the area of deep learning. Now, in some ways, the intellectual heritage and inspiration for this came back to this man, which I don't know if you know. His name is Santiago Ramón y Cajal. And he was a physician. He won the Nobel Prize in Medicine at the turn of the 20th century. And in addition to that, he's the father of modern neuroscience. And he was an incredible illustrator as well. And he created these beautiful diagrams of the brain, and he was the first one to, among the first one to really realize that in our brains we had these neural networks, these neural structures, that we had these cells, and that these cells called neurons had axons, and when axons intersected with one another, they formed synapses, and that the formation of these synapses were deeply rooted at the connection of memory and learning. It wasn't until then, the 1940s and the 1950s, that that very biological inspiration was abstracted, and the notion of an artificial neural network was created. Now, at the time, it wasn't the notion of a deep neural network, but the idea is conceptually very, very similar. in that we would start to see diagrams like this, with each circle represented a neuron, that neurons would be organized as a network of layers, that the connection between these neurons depicted by the lines will be the synapses, and that what we would have to do is to learn the weights, the strength of the connection between those neurons, and that could be sort of an overall and foundational architecture to do learning by example. What happened is that for a long, long time, it was a very elegant idea, an interesting idea, but it didn't work very well. And as many of you know, that whole process, particularly the neural network approach to AI, went through its ups and downs, including the field overall, with some AI winters, as it's been called, for a number of years during the decades. But in 2012, something interesting happened. And that is that the intersection of two other trends, the amount of computing power we had available to actually have this neural network with enough layers to perform the calculations and the training, and enough data, enough labeled data to be very precise on examples. And if you follow the field, you saw, for example, that if you look at the ImageNet competition and classification in the field of computer vision, error rates in 2010 to be able to perform the classification were on the order of 28–30%. And the largest improvement in the history of the field happened in 2012, and you can see what has happened in the progression over the last 5 years. So that's when it really began to work. And at its very essence, the core of the idea is that historically in the area of analytics, the idea of being able to represent the features that we were trying to analyze, whether it was in computer vision or in language processing, etc., were human engineered. But in this case, we can just extract the features automatically by providing it examples. And that there was a natural hierarchical representation of these features going from the input layer, it could be, say, the pixels that are being trying to use to classify, to determining the edges, the coordinates, etc., but they didn't have to be written by hand. It's a very, at its most simplistic form, what happens is actually quite straightforward in that you have an input raw of pixels, let's say x1 to x528 pixels in this case, and that at every neuron you have to make a decision as to whether the neuron is going to fire or not. Is it going to activate or not? And basically the mathematical operation that needs to take place there is just a sum of the value of the input preceding neurons multiplied by the weight of the connection between those two neurons. And you can have a nonlinear activation function that if it exceeds a threshold, let's say in this case it's 0.5 to keep it simple, the neuron will fire. And by having this nonlinear activation function and a high degree of connectivity, you have a very, very high dimensional space to be able to learn functions that you want to do. So fundamentally, there's two pieces of it, and we'll talk about it when we talk about hardware, that there's a training phase where one gives examples, and you are at the beginning, you're initializing the weights of those neurons, and you don't know exactly what the weight should be. And by giving it feedback into the networks, let's say in this case we're trying to learn digits, and we give it a 7, and it says, the system says it's not a 7, we say bad network, and then we send a signal back, we change the weights, and there's an algorithm to do that that got greatly more efficient in the early 1980s called the back propagation algorithm to be able to perform this minimization function. That is computationally expensive, and we'll talk ways to do that. There's another phase once the system has been trained, which is the inferencing phase, and that is computationally very cheap, because essentially what you have to do is this matrix multiplication, right? This multiply accumulate function. Okay, so that, and I forgive me if all of you knew all about it, but I thought it would be useful to have a foundation to be able to describe where we need to go, is with that very simple idea, a form of specialized and narrow artificial intelligence has begun to work. And that is the reason why over the last 5–6 years we have seen such dramatic progress in areas like language translation and speech transcription and language processing, etc. And the number of applications that one can do are quite infinite, and that's why there are so many startups and companies applying this core technique and the increasing availability of data and computation to do this. Now, what is happening also is that we're trying to see that end-to-end neural networks are becoming more and more capable. And they don't only have to perform one narrow function, now you can start combining things, and you can do things like not only image recognition, but automatically generating language or captions associated, for example, with an image. And here's an example of work we published last year, where you're seeing a few images, and you're seeing a single neural network automatically generating the captions of this. And you're seeing, for example, on the left, it says a blue boat is sitting on the side of a building, which is pretty good. Second one, it says a green bird is sitting on top of a bowl, which is also pretty good. And the last one, it says a woman sitting on a table with a giraffe, which is not exactly right, but to be fair, it's pretty complicated what's going on in there, right? So if we had to describe it, we would also struggle a bit to say it. Okay, so I'm not going to go through all the potential applications of it, but I did think that I would say a few words of an example we're using in the field of design automation. But the number of applications that even this very narrow form of AI you can apply is literally infinite. You've heard the quip of, software is eating the world. In some ways, these advances that are happening in machine learning and deep learning are partially eating some aspects of the world of software, right? And we're seeing how these functions are being embedded in every application. And I'll give you just a brief example of an effort that we've had for the last few years at IBM, and I'm sure so many of you are participating in different versions of this within your context, on how we can actually infuse some of these machine learning techniques to continue to evolve our ability to optimize circuit design. So, in our context for IBM, we continue to design and build very sophisticated microprocessors. And as this community knows better than anyone, the effort of still designing and taping out and executing a microprocessor is phenomenally difficult and expensive, where, a design cycle may last, 4 years, and you may have thousands of person years and hundreds of millions of dollars spent just for the microprocessor. And given that there's a renaissance going on in the world of hardware, and specific, hardware that we may want to apply for AI, increasing the degree of, the very purpose of this conference of automation and be able to do this more efficiently is extremely important and rewarding and valuable. And historically, we have seen that, one way to have dealt with the complexity in addition to software has had to do with, adding talent and effort to the overall process, which is expensive. So you can see some of the trends here in terms of the amount of project effort. So in this example was the intersection of being able to create an intelligent design flow that implements machine learning, and we created a system called Synthesis Tuning System, Synthesis, to be able to sort of run many parallel synthesis jobs in such a way that we could automatically learn the parameters that the experts were implementing in creating those workflows. And even though the software has improved quite dramatically over, thanks to, again, the community, what has happened over the last decades, the number of parameters that an expert has to adjust can be in the thousands, even with this software. So the question is, can you automatically learn those parameters through increasing effort of automation? And you see some of the example of our most, one of our most recent, chips for our mainframe for the Z13 system in 22 nanometer technology, where after experts had implemented the traditional optimization routes, by implementing a machine learning based system to do the configuration of these parameters, there was an improvement on the total negative slack of about 36%, 60% improvement on latch-to-latch slack, and 70% power reduction. So these numbers are very significant in the context that these were after experts already had done the best that they could with what they knew. So it's a good example, and I just give it, even in the context of this narrow form of AI, the applications, all I gave as an example is in the context of design automation, but I could have given you hundreds of other examples across industry. The number of applications is quite large. But we should realize that we're just in the infancy of where AI needs to go. So again, we're in this narrow form of AI. The bookend of this story will be achieving general artificial intelligence, which is quite far away, honestly speaking, right? The ability to create systems that can, learn and reason automatically, move across domain and learn across arbitrary spaces, it still remains a very difficult problem. And I'll say a few more words about that in a minute. And estimates is like maybe it's 2050 or beyond, but as you know, as scientists and engineers, when we put numbers like that, what we're really saying is we have no idea, right? How to do it. So in the meantime, then, that's what's very interesting to say, well, what's going to happen? How does AI need to evolve? And we've defined this category of a broader form of AI. And I'd like to share with you a few thoughts around that. Undoubtedly the case that for a single task on a single domain, if you have enough labeled data, you can achieve superhuman accuracy in performance. There's no doubt about it. However, the moment you got to perform another task or another domain, you got to create another neural network, again, from scratch and train it. So our ability to be able to create neural networks, and I'll talk about some other techniques in a second, that can grow across tasks and domain with more modalities of input, more distributed in nature, not only centralized, but also at the edge, and more explainable, are sort of core characteristics of where AI needs to evolve. So if I were to summarize that agenda in one chart, I would put something like this. I would say that, and these are all major fields of endeavor, right, with very, very large efforts on each one. But we must create AI that is less of a black box, that is more explainable, that we have a better understanding of what is happening in the neural networks, that we have debuggers for our neural networks, and that we can actually deal with the errors that are present on those networks. By the way, explainability is very foundational for the application of many industries. It is okay to perhaps use a black box when you're using a recommender system for, what books you should buy or so on. But when you're using it in the context of high-stake decision-making, where there's a lot of investment or the decisions have high stakes, a total black box is mostly unacceptable to so many professions and so many areas. So this is an area that is very foundational and very fundamental. The second one is that it is very impressive what some of these neural networks can do. But if you know about them too, they're very fragile. And if you've seen the emergence of adversarial networks and the presence of GANs, how you can inject noise into the system to fool the system into classifying an image or fooling in how it detects the language of the transcription, it actually tells you the fragility that is inherent in these systems, where you go quickly from recognizing something looking like a bus, and then you inject some noise and it says it's a zebra. And you're like, and it's kind of hilarious when you look at it, but again, if it's high-stake decisions, it's a problem. Furthermore, you can poison these neural networks. They're subject to all sorts of attacks. So the whole area around security of artificial intelligence is very, very important. Ethics. Boy, this is a big, big topic. And before we even talk about notions of superintelligence, I'll tell you an area that I'm really preoccupied about, which is bias. The introduction of bias on these neural networks. If you create a system that gets trained by example, if the examples that you use are biased from the past, let's say credit decisions that happened in the past, and the lesson that the system could learn could be don't give credit to minorities or don't give credit to women. And that is a terrible situation. If we take the biases that we've had in our societies in the past and we encode them, automate them, and scale them out. So there's a very, very fundamental piece of work that needs to happen with who trains these systems. What are the standards and the requirements? How do we verify that they're bias-free? How do we inspect them? So there are a lot of important implications to the ethical dimension in AI, and I just touched on one. Another one, well, it's great that you can learn by example, but boy, why do we need so many examples? Right? Why do we need to teach it 10,000 examples or 100,000 examples? We need to be able to learn with less data. So to learn from less data, simply put, one has to have prior knowledge. And to have prior knowledge, there's a field of, for example, you can do techniques like transfer learning. You learn in an area the weights of your neural network where you have a lot of data, and then you transfer some of those weights to another area where you have less data, so you can learn more selectively. So that's one way. But the other fundamental thing and a core area of where AI is going to go is the combination of learning and reasoning. Now, learning has made a lot of progress recently because of deep learning, but reasoning less so. So in some ways, the old-fashioned AI, right, of logic and logic representation made contemporary and brought closer together with learning has to be part of the future of where AI needs to go. because we have to be able to accumulate knowledge and reason over knowledge, not just learn over past data to be able to get to the next step. And finally, we gotta continue, and I'll talk more about this, about the infrastructure. The recent advances in AI have been enabled by computation. And there's a wonderful roadmap ahead, and we live in a moment of hardware renaissance with a lot more creativity is possible with new architectures, thanks to specialized workloads like deep learning. So, a few words on general AI. I would broadly say, and I'm gonna stylize a summary of a very complex field, that there's sort of like three major threads of articulating how we may get to a more general form of AI. One is very hand-wavy, but interesting to some degree, which let's say is like the exponential story. That's like a Ray Kurzweil story, right? Where he says, look, there's all these exponentials going on, exponential amount of computing power and data, exponential growth of the number of scientists and the accumulation of knowledge, and the intersection of those exponentials eventually, right, will produce something revolutionary. They would say, hey, you know, look at deep learning, right? It was the intersection of two other things that made it work, so why wouldn't that happen more broadly? Like I say, a little hand-wavy, but an interesting trend. Second one is reinforcement learning. It's a story of saying, well, if you have a loop where you actually have a reward function and you have enough instrumentation of an environment and you can learn from it, maybe you can do reinforcement learning to find and bootstrap your way to acquire general knowledge. You have all seen this applied in the context of games. It's very impressive because you can have a self-contained universe where you can experiment at low cost and with low consequence. And indeed, you can learn new functions. But it's tricky to do in the real world, right? Because experimenting in the real world is neither low cost nor no consequences. So that's a second threat. The third story is to say, look, no, to get to general intelligence, you have to accumulate knowledge. And you gotta have persistent knowledge representation of your world. And you gotta be able to reason over that knowledge as well to be able to get you there. And you can see how all of these things will be trends that intersect with one another. But I thought I would give you some sort of milestones so that if you see these things happening, perhaps you can see that some inflection point is taking place. So we've gone from the world of rules and being able to do the feature extraction by hand and so on. We are in the middle of living the world of, in AI, of like the convolution neural nets and reinforcement learning and things of the sort. So we've seen that, and that's what we're all using today. I've talked about how the next step in broad AI has to do with how do we transfer learning more broadly and, and be able to extend the compositional aspect of AI. But these next two steps are really, really hard, which is fundamentally, can we really, really make a difference and crack the issue of reading comprehension? Can we, not language processing, I mean, can we build a machine that really comprehend a text and understand what it says? And the second companion of this is, that would be the equivalent of reading. The second component is, can we really crack the issue of automated programming, which will be the equivalent of writing for humans? If those two things happen, which are so difficult, some may argue that those are AI complete problems, that cracking that problem you have to solve general AI. We'll see. But if real progress happens on those two, that will be a very dramatic inflection point. And the third step, you can imagine then that to the degree that these systems would have access to experiment in domains, if they could do automated experimentation, but now they have the ability to learn and read and write and experiment with something to fill the gaps of knowledge, now you can get into a different situation. So people are working hard on these things, but they're phenomenally difficult problems. Now, one of the things the field does is it puts grand challenges forward to sort of illustrate what is possible to do with computers and to tell us where we should go next. And you remember, you may have heard through your history, like, for example, Arthur Samuel, who incidentally, while working at IBM, coined the term machine learning. He was the first one to create a program, a machine learning program, that played checkers. We saw how in the 90s, we created a system called Deep Blue that played Garry Kasparov and won. We saw in 2011 creating a machine that played on Jeopardy, right, to tackle the question of open domain question answering. And we've seen recently also reinforcement learning applied to learn how to play AlphaGo. Now, I'll point out, too, that Jerry Tesoro in the early 90s as well had demonstrated using reinforcement learning to play backgammon, right? So there is a notion also of, this is to make a point of how computing power, like if you added these ideas, you can keep doing more and more complex things. So after we did Jeopardy, we asked our research team, our research scientists, to basically say, what would be an interesting challenge to tackle on next? And there were many, many proposals across the division. But the one that we ended up selecting and won was something called Project Debater. And there was a researcher in Haifa, in our research lab in Israel, who proposed this idea that, like, well, we've been doing games and things for a long time. It'd be very interesting to evolve AI in a direction where is no clear black and white winner, where AI had to deal in a much more nuanced and ambiguous nature of human decision making, and debate is an interesting space of it. So last week, as it happens, we had the first sneak peek. We've been working on this for 6 years. And this first sneak peek that we show a group of like influencers and journalists and so on in San Francisco, actually, was Monday of the previous week, on something called Project Debater. And you'll hear a lot more through through the rest of the year. But basically, we have built a system that debates a human. So given a motion, it has to construct automatically a 4-minute speech. The human gives, their counter argument on the debate, a 4-minute speech. The system has to be listening to that. It has to understand what it says, create a rebuttal, which is another 4-minute speech. The human then does their own 4-minute speech, and the system has to create their own closing arguments for 2 minutes, and then you can evaluate, how the system do. So let's roll a short video of the project.
Real-world problems, a lot of times they don't have a clear bottom line win, otherwise we wouldn't debate things.
According to rules set by the candidates themselves.
What we are trying to accomplish here is really to demonstrate that we can have a meaningful and valuable discussion between man and machine.
We are actually trying to show that a computer system can add, if you want, conversation or decision making by bringing facts and doing a different kind of argumentation.
Hello, Dan. Thank you for the opportunity to be here today.
The debater system tries to understand the concept over which we are debating.
Having analyzed the data, I will argue that we should subsidize music education.
When it gets the topic, until you hear the first speech, it's collecting all the possible arguments, trying to remove redundancy.
It is about recognizing important issues for society.
The system is evolving.
The IBM debater can have all the opinions in the world, but IBM debater does not pay taxes, and we do.
You are speaking at the extremely fast rate of 218 words per minute. There is no need to hurry.
The value of the technology is really to allow decision makers to take more informed decisions. There is a territory which is uncharted to some extent, and this is where we are now.
Thank you for listening.
So look it up, and you'll hear a lot more about it. But it should be really fun. So I'd like to take the remainder of my time to talk about hardware and the physics of AI and where computation needs to go in the context of the promise of AI that we just discussed. And here's a roadmap that we are envisioning. First of all, we see orders of magnitude of improvement possible to accelerate AI. We obviously have the traditional CMOS-based technologies. Today, the reigning paradigm for training are GPUs. For inferencing, we still do most of the work with CPUs. And we see a roadmap where approximate computing systems will be implemented with reduced precision that will give us, quite a bit of leverage. There'll be a second, roadmap dimension, the second row, that has to do with the introduction of novel device structure beyond the traditional transistor, perhaps novel memory devices in the context of computation that will get us a long way. And the third one I'll discuss is also quantum computing for AI. So let me give you a little bit of highlight around that. GPUs today you can do distributed training with large amount of GPUs. At the extreme of it, I'll give you an example. Recently we announced the world's largest supercomputer that we had built. And it gives you a limit of how many GPUs. So we built a system that has 27,000 GPUs. So lots that you can do, not that you can distribute that amount of training over that many GPUs. We've demonstrated that you can do it over 500 or 1,000 GPUs, but still, we all know that that is the reigning paradigm today. Just a quick reminder of why there's so much possibility to create new architectures for this, and that is because the type of computation we have to do for this is quite straightforward, actually. Fundamentally, we got to do this multiply accumulate function that happens at each neuron, right? To be able to do that, there's an activation function, and then there's a matrix, a weight update, right? So I have to learn the new weights and update the weights. So pretty straightforward. So here's a roadmap of what things could look like, and I'll give you a few examples. So we're basically seeing that the improvement in terms of gigaflops per watt for deep learning, it is improving at 2.5x per year. So within a decade, if you think deep learning and things like that are being used, just think about the fact that the cost of building a neural network model will drop by a factor of 1,000. So we're going to have models that are going to come out of our ears, right? So one thing is reducing the precision. Actually, the beautiful aspect of neural networks is that they're fairly tolerant to error. So why do you need floating point operations? And we published in ICML in 2015 example of using limited numerical precision. It's something that is being very broadly adopted in the industry right now. We demonstrated at the time that you could use 14 bits of precision and achieve the same level of training accuracy than with floating point. In fact, since then, we demonstrated you could do this with 8 bits, and people have done it with 4 bits, and so on. So reducing the amount of precision in our architecture for implementing the neural networks, it's a smart way to go, and you can have lots of savings in terms of area and complexity in these systems. The next step is this category where I start referring to as the physics of AI, have to do with actually touching the device and doing something novel there. So one of the things that you can do is traditionally, we of course have to store the weights in memory, right? And you're doing the multiply accumulate function, say in a GPU. Can you actually bring the whole aspect of memory and computation closer together? It's an old idea of using like systolic arrays, but basically, since you have to do this multiply accumulate function, you can imagine that the first column of the peripheral circuits represents the first column of the neural network on the left-hand side. The pink row represents at the bottom, the horizontal line represents the second column in the neural network. And obviously, since V equals IR, if you send variable voltage pulses horizontally and you read the column, you get, and you have a variable resistance that can store the weight, you get the multiplication for free. So the trick here is to say, I want to store the weights of my neural network in my unit cell. And how can I do that? Well, there's many ways that you can do that. So one straightforward thought is to say, can I use memory cells to be able to store the weights? But you notice immediately that you have slightly different set of characteristics compared to traditional devices. In that, in a memory cell, traditionally you just have a 0-1 state. You need very high response times of nanoseconds. The high-low, maybe a factor of 10,000 gaps. And the shape, meaning the symmetry of going from high to low, actually doesn't matter, right, in a memory thing. However, in an AI cell, the situation is slightly different, right? Where you want incremental control, so going from weights at 0.1, 0.2, etc. It can be much lower, and the ratios can be factor of 10, and you would like the signal to be symmetrical, right, of going up and down. So one way to start is obviously to use devices you already have. We've been working on phase change memory for many years, as you know, as a community. And here we have been also working for a number of years on this in IBM research. And we've built chips now with over 1 million PCM elements and demonstrated that you can implement deep learning training with 500x improvements compared to what you can do with a traditional GPU with similar levels of accuracy. We've also recently published at Nature Electronics a hybrid mixed precision system. So some of it can be at a very, sort of low precision but very efficient calculation that happens with the PCM matrix array. but you also have some high precision digital logic to be able to, at particular moments of the calculation, be able to fine tune and get the arbitrary precision that you need in the calculation. We've demonstrated this with over 1 million PCL elements and 10,000 systems of equations and be able to demonstrate that. And finally, you want to be able to develop a new material, and I will point you to this paper that did a really rigorous work of demonstrating if you wanted to devise, to create a novel material that it was ideally suited to implement deep learning and neural networks, what would be the characteristic of the material that you would need to create? And I recommend that you read it in some detail because it may give you some insights of what we need to create as a community. But one of the things to highlight is this idea of symmetry of, in this case, we would like to be able to have this control resistance to be able to store the waste with good symmetry. And we've recently built a prototype, actually leveraging expertise that we have in hafnium oxides and designing these materials to show this kind of symmetric switching property behavior for neural networks. Okay, so let me take just the last 5 minutes to share with you a little bit sort of even more exploratory dimension, which is quantum computing applied for AI. First, I'll just readily acknowledge that quantum computing is kind of like in the stage of the 1940s and 50s of computers, right? So you see pictures like this. This was Colossus, the machine. And this is what a quantum computer looks today, right? It's kind of similar. This is one of our labs in the lab that I show you where I work in Yorktown Heights. And so let me give you the idea of why this may matter for machine learning. So we've all gotten used to this idea of you can have neural networks to give an input vector and perform classification on a yes or no question as an example. And I want to sort of present to you that you can have another machine, now that we have that kind of abstraction and people have gotten used to it, you could have a quantum system, a quantum circuit, that the sort of high dimensional space that is available to you to learn a function is just different fundamentally in nature compared to a classical machine. And that the distinction is that the dimensions that you would require classically to model that quantum circuit would be exponentially costly if you did it with a classical machine. And that property that is exponentially costly is this idea of quantum entanglement. And it's a resource for which there is no classical analog. You will recall that at the root of this idea of entanglement is connected to the Heisenberg uncertainty principle. And we all learned that idea that if you have a particle, you cannot arbitrarily know the position and its velocity, really its momentum, with arbitrary precision. If I know exactly where the particle is, I don't know how fast it's moving, and if I know exactly how fast it's moving, I don't know where it is. So you can have this thought experiment where you can take two particles and you entangle them. You will see that in our case, two entangled elements are the qubits, but the idea is the same. You take the two particles, you entangle them, and if you separate them to the ends of the universe, what entanglement really tells you is that if an observer go in and measure one of the particles on these extremes of the universe and determine its position or its speed, if we later compare notes to somebody who was observing the other particle or nearby, we would have seen that the act of measuring the position or speed would instantaneously allow us to determine the position or speed of the other particle. And that is a very weird phenomena that either tells us that somehow we can communicate across the ends of the universe faster than the speed of light, which we don't believe is true, or that a quantum description of the world is fundamentally more complex than everyday experience tells us. And what it fundamentally violates is this principle of non-local action, right? So non-local action is possible in our universe if you have entangled particles. And that idea is something that Einstein never liked, right? That's the one he criticized, calling it spooky action at a distance as a criticism. But he wasn't right about that. So this resource I mentioned is computationally expensive. So there's a connection between this physical mechanism of entanglement and the world of information. And this is a description of that if you had two qubits that were entangled and you had to represent them with a string of bits, it would be exponentially costly. Meaning with 2 qubits, it will take you 512 bits to represent them. With 3, you double, So every qubit you add, you double the number of bits you need to represent. And by the time you have 100 entangled qubits, you need more than there are atoms on planet Earth to represent. So that's what I mean that is costly. So a quantum computer has a string of bits as inputs. It represents information in 2 to the n states, where n is the number of qubits. And in the end, when I perform a measurement, it comes out as a string of bits. They're beautiful machines. We use superconducting technology at IBM to create our quantum machines. And they are like, incidentally, as I said, the most beautiful machines we've ever built. They operate at cryogenic temperatures. In our case, our quantum processor operates at 15 millikelvin. So it's about 100 times colder than outer space. And we use a new device called a transmon qubit, which is an anharmonic oscillator. It's based on a Josephson junction. And basically, you create an artificial atom where you have a well-controlled ground state and an excited state that you control by sending microwave pulses at the 5 gigahertz range. And that's how you actually both perform the initialization of the system, the entanglement across the qubits, and the readout functions of it. So I want to show you an example of applying this to the field of machine learning on an experiment we just recently conducted. The connection between dimensionality and classification is well known in mathematics. If you have a linear two dots, light blue dots and dark blue dots, and you need to separate them into 2 classes, if you only had a single plane that it's allowed to be able to do the separation, you know that on the left-hand side, on the 1D function, you cannot draw a single line to separate those dots. But by curving the line, we can find a plane that separates the light and the dark. Same idea, but now you can make it an arbitrary number of dimensions. So a lot of problems in machine learning has to do with mapping it to a high-dimensional state and find a hyperplane that separates the classes. So you can do something similar with quantum. So in this case, we use the way an algorithm works in quantum is I initialize my computer in a superposition of states. If I have 2 qubits, it's 2 to the 2, so that's 4 states, 0, 0, 0, 1, 1, 0, 1, 1. Each state is represented by an amplitude and a phase. Injecting the problem into the quantum computer means changing the phase of my states, and an algorithm is the evolution of those states to interfere with one another to give me the right answer. So here's the experiment we did with machine learning. We had a 2-dimensional array of dots, gold dots and black dots. We're going to use a quantum network, a quantum circuit, to be able to learn that function. So in this case, this is the training set. The function we're trying to learn is that one. So later, when we see dots that are in the black region, they should be labeled black. When there are dots that are in the gold region, they should be labeled gold. But at the beginning, I only have my training examples. I don't know the function. I'm trying to learn it. So you implement an algorithm that, that's a depiction of how it's written. We don't have to go into the details of what that is. And here's the experiment. We get a new set of data. We need to label it black or gold. We haven't seen the data before. And here's the result experimentally in our quantum computer. We show that the classification accuracy with which we can assign labels improves to 100% in this case, or close to 100%, as we increase entanglement. So what we have proven experimentally right now is this special property that only exists in quantum computers, entanglement. The more I have it, the lower my classification error. And that's pretty exciting. So the future of quantum is about increasing the number of qubits and reducing the error rate of the qubits. And that is what we define as quantum volume. So the roadmap of quantum computing is to go in this diagonal of going from the current state of 50 qubits, 20, 50 qubits, and so on, and lowering the error rates from a few percent to 0.1%, and eventually getting to a fault-tolerant quantum computer. So I'll close. This is what they look like. We operate now many working quantum computers around the world. You can experiment with them. We have 3 available for free to try, for people to learn. It's called the Ibm Q Experience. And we've had over 85,000 users all over the world trying and learning about this. There's been over 85 scientific publications using these tools. And I'll give you a little map of 5 days of people all over the world using our quantum computers. These are not simulations. These are running on quantum processors, right, in IBM. And it's a beginning of a new community, so I would encourage these communities, early days, okay? But I would really encourage you to start thinking about like how do you learn about quantum computing and how you may be able to exploit it in the future. So I'll close with this quote from our head of theory at IBM Research for Quantum. Then we were having a meeting about a year ago, and we were talking about, you know, there's a lot of faults that one can get in drawing false parallels with classical computing. And at some point, he got really frustrated about the way algorithms were being described, and he said to us, "You're thinking too classically." And it's become kind of like a motto for us that you gotta actually think differently to be able to exploit its properties. And I hope you'll get a chance to give it a try, and I really wanna thank you for your attention. Thank you.
Thank you. Thank you so much for that wonderful talk, going from broad and depth. And I think he showed us the algorithm side and the hardware side. And we, in the design and automation community, I think we are here to bridge that gap. I think there's great opportunities. Let's thank Dr. Gill again.
Thank you. Thank you.